So, good afternoon, everybody. It's a pleasure to me today to have with us Professor Markus Reiher from ETH Zurich, and I thank him again for being so kind and accepting my invitation to come to Brazil virtually. I hope soon we can be here in person. So just a brief presentation about him. He got his diploma in chemistry in 1995, PhD in 1998, habilitation in theoretical chemistry in 2002, and private docent at University of Bonn in 2005. And then he got a series of chairs of theoretical chemistry in different universities. And since 2006, he is working in theoretical chemistry at ETH Zurich. And 2011, he got the degree of full professor. I think that's what Ordentlicher means. Am I right?
Okay. Absolutely.
Okay.
This is what it means.
Okay, thank you. So he also has a lot of awards. I put some of them here. And maybe in 2018, one of the most recent award, Lovdin Lecture in University of Uppsala. And also he got the best teacher award from Credit Suisse. So he's a very good teacher also, besides being a very good researcher. Among his several research interests, I highlight relativist quantum chemistry and atomic physics, electron-electron interaction and dynamical correlation with developing methods like DMRG and DFT, theoretical bio-inorganic chemistry and coordination chemistry, quantum chemical analysis of novel compounds, vibrational spectroscopy of large molecules, and new ways to explore the quantum reactivity by using quantum chemical methods. He has also been developing a lot of softwares. He is among the co-authors of OpenMOCAS. He has also been working in a software for chemical interaction networks for studying chemical reactivity. A new interface for exploring the chemical reactive in a very nice way on your screen. It's a very nice, in the paper you have a very nice view about what this program can do. He also developed the AutoCAS. It's a graphical interface to automated identification of orbitals that is very helpful to select active space. Markus, that it's the interface for run DMRG calculations in MOCAS and many other programs. And maybe one of the most used by us is DKH, is the way we introduce the Douglas-Crowe has spin orbit effects in SeaWorld during MOCAS calculations. That's, I think everybody has been using it. And he also has a lot of publications, about 300 papers, an index age 62, and more than 16,000 citations. And I put here on the right side two books. One of them, he was the editor of this book published in Topics of Current Chemistry about approaches in modern biology. And one that maybe it's more used by the students. It's the Relativist Quantum Chemistry. It's on the second edition. So during this seminar, I ask you, please keep your microphone mute. And I put here questions at the end, but I don't know what do you think, Markus, if they can ask you during presentation. I don't know. What do you prefer?
Of course, you can interrupt me anytime if you wish.
So if you wish, please interrupt him. And I'm sure that everybody will enjoy your seminar. So thank you very much, Markus, for being with us today. Thank you very much. I'm just going to close my presentation so you can start yours.
Okay, I switched to my slides. Before I do so, thank you very much for the very kind introduction, and of course for the invitation. I mean, I think this is the most embarrassing introduction that I ever received. And of course, the expectations are high, so I hope that you won't be disappointed, but we will see. I should switch to the screen. Yes, that should work.
Yes.
Okay. Now you should see my slide again, my title
Yes.
slide, right? Okay, as you can see from the title, I'm going to talk about electronic and vibrational structure problems, and eventually even end up at talking about quantum dynamics, and that will all be in the context of matrix product states. And matrix product states are specific, and of course I will introduce you to matrix product states, but they are a specific approximation to the many-particle problem in quantum theory that are optimized by the density matrix renormalization group algorithm. And so before I go into the details of the latest research that we did in this area, I will give you an introduction into this DMRG algorithm and into matrix product states. And we start at the very foundations, right? So what we intend to do in quantum chemistry is to solve the typically time-independent, but occasionally also time-dependent many-particle Schrödinger equation. Now, I don't know whether you can see my pointer. So the time-dependent equation here is on the left, which is the energy eigenvalue problem, and on the right, the time-dependent equation. Of course, time-independent means you can tackle ground state properties. Time-dependent means that typically you would go for non-equilibrium processes and some sort of perturbation, for instance, by shining light on a substance. And of course, in order to solve these equations, you need to choose a Hamiltonian, right? And I give you 3 examples. For the electronic structure, we have the electronic Hamiltonian, which is very well defined in terms of the interactions. We have these pair interactions, which are in the non-relativistic regime, exactly given by electrostatic Coulomb interactions. And of course, you know that the singularities there cause a couple of problems for solution methods. Vibrational structure problems are much more complicated because the interaction operator is given by the electronic energy, which we somehow need to approximate, right? And that is typically done by a Taylor series expansion in terms of some coordinates. And then, of course, we are interested in the coupling of the 2 dynamical degrees of freedom, electrons and nuclei, which leads us to vibronic problems. And typically you consider model Hamiltonians to describe such processes, and I will discuss an example later on. Okay, so these are the Hamiltonians. How do we construct the state function to solve the Schrödinger equation? Well, typically what we do is we choose a single particle picture, right? Because a single particle picture is can be well described, and we have a systematic way to construct the many particle picture out of the single particle states, and that is through tensor products. As a result, if we have chosen a single particle basis, for instance, molecular orbitals, we can construct an occupation number vector, right? That is given here as this ket. And what we denote in this occupation number vector is which of the single particle states are actually occupied. Now, if we take each of these occupation number vectors to form a basis for the expansion of the total state, you see here there's a subscript vibrational, but that also, of course, holds true for the electronic state. So any many-particle quantum state can be expanded into this set of all occupation number vectors, right? And then, of course, in front of it, you do have an expansion coefficient, which typically is called a CI coefficient, right? And you see already here that rather than having a single index for the CI coefficient, because I could simply number them, I have resolved the single index to show that it is a high-dimensional tensor where the single index is to be understood as a composite index that is made from all the occupations of the single particle states. Now here you see a graphical representation of the whole problem. Right? So we have this fat red bar, which represents our CI coefficient tensor. And hidden in here without any resolution and always the same weight are the single particle states. Right? Just as an example, I picked molecular orbitals here, only for illustration purposes, because it would work equally well for vibrational modes. So there's no hierarchy that's introduced. And what we do next is we focus on one of these single particle states. So we have kind of a local view, although this is a highly complex high-dimensional tensor. This local view, so picking one of the single particle states, creates a system environment separation. So what is now in this box is a system. It's a single orbital or single mode if we talk about vibrational problems, and the rest is going to be the environment. Now here you see a change in the graphical representation where I emphasize that I now focus on the single particle states. And I have also rewritten my configuration interaction expansion. It is, in fact, it is of the same type as what you have seen before, but the occupation number vector is now decomposed into 3 components. But remember, it's the same expansion. But with a focus on one of the single particle state. I picked this one, which is highlighted here in red. And then there are, of course, other single particle states to the left and more to the right, which need to be taken into account. And of course, the sum that I had before is now decomposed into 3 classes of sums. One for the states that are defined on this single particle state that we are looking at, and then a sum for all the states that are defined, many particle states of the subsystem defined on the right hand side and to the left. And if you want to see that pictorially, well, before you had this fat red bar, and now there's a blue bar, which is a little smaller, but of similar complexity. We have our individual state, which is a red circle. Then, and on the right hand side, we have the all the many particle states which are missing in order to construct the target state out of these 3 components by tensor product formation, as you can see in the equation. Okay. Now, of course, nothing has been gained yet, right? Let me go back. Nothing has been gained yet. The dimension is the same. The dimension grows exponentially. Say, if we look at orbitals, and the orbitals I depict are spatial orbitals, then I can have 4 states, and that's also the reason why this sum runs up to 4. We have 4 states per single particle state, and say if we have 100 single particle states, 100 spatial orbitals, then we have 4 to the power of 100 in dimension. And of course, this is the representation of the curse of dimensionality, which eventually kills off everything that is computational possible and restricts us to deal with active spaces that are smaller than, say, 20 orbitals. So this explosion in dimension is, of course, an issue, but this picture already includes the key to deal with it. And that is, we could restrict the number of states that are defined to the left and to the right. And now if you look at the equation below, you see that I have reduced this 4 to the power of number of orbitals to the left and 4 to the power of number of orbitals to the right to m. M is a key parameter in what we are going to do. It's called the bond dimension. And the idea behind this is that not all of these many particle states to the left and right are going to be important for the final state. Okay, and reducing the large number to the small number m also makes it computationally feasible. Now, what we have done for just one side, the third one, we can do for each of them. And then the total CI coefficient is actually decomposed in this sequence of matrices. Right, so everything what we have done, let me go back. You see here in this equation below, there is this parameter now, which has 3 indices, because one index holds for the state because of the orbital that we explicitly picked as a system. And then there are 2 more indices for all the many particle states to the left and to the right, so which are defined on those orbitals to the left and to the right of the orbital that we are looking at. Now, if we consider each of the orbitals in this way, we get this picture, and that eventually gives you a sequence of matrices M, which are to be multiplied to give you the CI coefficient. And so in order to get a scalar, of course, the first and the last matrix need to be vectors. Yes, and this is in fact the matrix product state representation of our many particle state. And the idea now is to find an efficient algorithm, and DMRG is this efficient algorithm, to optimize the sequence of matrices. Once we have done that, once we have accomplished that, of course, we know the CI coefficients. Okay, there's some terminology that is popular in the DMRG community, and that has to do with the fact that the algorithm was developed originally for spin lattices. And so these single particle states, they can be orbitals or modes. They are called sites, and all the sites, they form a lattice, right? And of course, you might wonder how you put the single particle states on the lattice. And in fact, that is a choice that you make, and this choice affects the convergence. I will later comment on how that can be efficiently done in a reliable way. The reduced basis, so which only use small m, the bond dimension, number of basis functions for the left and right environment of any given site, is called the renormalized basis. Okay, now if we want to compute an expectation value, for instance, the energy, of course, we need to be able to form this bracket, right? And it's now convenient to represent what's going on in terms of a picture, as you see here on the right-hand side, where the bra is represented here by the matrix product structure indicated in green, and the cat so the same structure indicated by red. And you see something is missing in the middle, and that is, of course, the Hamiltonian. But before I tell you more about that, this picture directly relates to the mathematical form of the MPS, where you have one free index that can now be contracted with the Hamiltonian, or with the operator in general for an expectation value. Now I have inserted the Hamiltonian, and the Hamiltonian can be simply written in this form, right, where we have the occupation number vector, sigma prime here. But to do that in this way is not at all efficient, because we have this local structure where in our wave function parametrization, we explicitly have parameters that are labeled according to the individual orbitals or modes. And therefore, it's more efficient to have a formulation of the operator that is called the matrix product operator formulation. And DMRG programs that follow this formulation, we typically call second generation DMRG programs. Here you see this formulation, right? So it's again the Hamiltonian, but now you see that, let me go back, rather than this W parameter in front of that cat bra structure of the basis, you now have a sequence of parameters, H, which are associated with the local sites in this cat bra structure. And by contrast to the MPS, which is an approximation, since the bond dimension M is typically not, it's finite and not of the size that allows you to represent a state exactly. This representation that you see here for the operator is exact. So the matrix product operator formulation is always exact. And you see also that this, now you have this site structure where the label is, as you see here in the middle, is to specific sites in the lattice, and that is then pictorially represented by this sequence of boxes given in blue. Okay, now, say if this is the energy and we want to optimize the wave function variationally with respect to the energy, we can do that iteratively, and these iterations, they are called sweep optimizations. And the sweep optimization, I will give you an example later on, basically solve for each site a local eigenvalue problem. And so you start, for instance, on the left doing this, go to the next site, solve the local eigenvalue problem, and proceed until you reach the end of the lattice. And then you change direction and you go back. On your first way to the right, all the information about many particle states in the right block are actually missing, and those you need to guess. When you return, so you switch direction, everything that you have done in the first sweep to the right, you have stored and you take as an approximation. This way you sequentially optimize the energy. Now let's look into the Hamiltonians that we are interested in. Here you see the standard electronic Hamiltonian in second quantization, the 1 electron term, the 2 electron term. And the key features of this is that the interaction is complicated. It has 4 indices, but it's well defined, not more than 4 indices. We follow Fermi-Dirac statistics. Occupation numbers for our orbitals, spin orbitals in this case, can only be 0 and 1. Whereas for the vibrational Hamiltonian, it's more complicated because, as I mentioned before, we need to expand our potential energy operator, which makes it complicated. Typically, the expansion is truncated, yielding in second quantized form terms that have more than 4 indices. So these are more difficult to treat and require actually a computer program that can easily handle Hamiltonians with terms of arbitrary number of indices. And in fact, our computer program can do that, and therefore it was easy for us in our MPS MPO program to implement this kind of Hamiltonians. Of course, when you consider vibrational problems, and I'm not going to talk about that, the potential energy surface is typically not known. So getting this surface and then obtaining the Taylor series expansion for that surface is a totally different story that I don't want to, I will not touch upon here in this context. Okay, and then of course, now we follow Bose-Einstein statistic. Apart from the fact,
Markus, sorry,
yes.
Roland has a question for you.
Yeah, just interrupt me because I only see my slides. I don't see anybody.
That's fine. You're doing well. I just has on your second point, you say the standard choice is a Taylor expansion of the potential.
Yes.
Have you or any group been starting to use the Gaussian process regression to actually have a surrogate model of your potential?
Yeah, people are doing this, and so probably Joel Bowman has done that. He has looked into these machine-learned fits to potential energy surfaces, but I guess that also other people are working on this.
And does this offer some better way of does it remove any bottlenecks?
It's difficult to tell. So what you're suggesting basically means that you have your machine-learned representation of the potential energy surface in position space, which you now need to transform into second quantized form, and then it depends on basically on the number of indices to each of the to each and every one of the terms. But I haven't thought that through. I don't know how that looks like. I need to think about. Maybe it's worth doing this. We have not done that because, as usual, I only have a very few number of people working on the various topics, and well, it's so natural to do that, but for time reasons, we haven't.
Okay.
But we should keep that in mind, Roland.
All right. Thank you.
Okay, so here, this slide collects a few essentials on DMRG. So there's this high dimensional CI coefficient tensor that is decomposed as a product of lower dimensional matrices. Because the dimension is reduced, it's an approximation, but the accuracy and efficiency can be controlled. This is why it's called a matrix product state. The full diagonalization of the CI problem is replaced by a series of local eigenvalue problems, which you iteratively improve through sweeping. The whole approximation is variational. The accuracy of the whole approximation is controlled by the single parameter m, the bond dimension. And of course, the full CI limit you would recover in the for m goes to infinity. So strictly speaking, the advantage is that we have a polynomially scaling method as long as m can be kept finite and does not grow. It turns out that for vibrational problems, M is surprisingly small. For highly correlated electronic structure problems, M can be as large as 10,000. Now, a quick picture of the sweep-based optimization algorithm. On the right-hand side, you see this energy representation with the local resolution. And we start on the left-hand side and then go through the lattice, solve these eigenvalue problems for each lattice side. And on the left-hand side, you see a green line emerging, which gives you the energy. This is actually for a vibrational problem. And then once I'm at the end of the lattice, I switch direction and go back, and then back and forth, and you see that the energy is converged. Right? This is the way DMRG optimizes the parameters in the matrix product state representation. Okay. Now, after this introduction, let me switch to a few recent applications. They deal with the vibrational problem because...
Another question, sorry.
Yes, sure.
This nonlinear expansion, there must be multiple solutions. How do you sort of handle that so you don't have, you know what I'm talking about?
Yeah, I know what you're talking about. It's a problem. It's a huge problem. There are two solutions which prove to be efficient in practice. So first of all, what I show to you is actually the single side DMRG. You can leave two sides explicit. So instead of having 4 states explicitly represented, you have 4 by 4, so 16 states explicitly represented. And that makes the whole ansatz more flexible and avoids convergence to local, to solutions which are minibar, but higher in energy than the solution you're actually after. And then the next thing that there are more factors, of course, that determine whether you end up in the wrong solution or not. One is, of course, if the bond dimension is too small, that can happen. But a key is that you need to arrange the single particle states properly on the lattice. And of course, that needs to be done without too much additional effort, because otherwise it would not be worth the effort. And what turned out to be efficient, and that is what Legeser has figured out already 15 years ago, you can compute entanglement orbital entropies and then put those single particle states that turn out to be most entangled. So for instance, those orbitals that are responsible for all the static correlation in the middle of the chain, in the middle of the lattice. And that solves a lot of the convergence issues. In fact, if you do that, then you will hardly witness any convergence problems. Whereas if you don't do that, what people did before, and I don't know whether anybody is still doing this, you could, for instance, perturb a reduced density matrix that is used to select your the reduced number of states, and that shall make sure that you don't lose basis states that will later become important for the optimization. There can be any perturbation like white noise, or a perturbation that has been an analytic perturbation formula that was proposed by Steve White in, I think, 2005. But what we do is we use these entanglement measures when you use QC. When you use QC Markus, you should watch out, because that starts typically by default with an energetic ordering of orbitals, for instance, and you need to explicitly switch the ordering according to, which is called the Fiedler ordering. You will see that later on. You should explicitly switch that on.
So usually when you have a CI code, you're doing cos-SEF. You don't optimize the orbital and active space, since the energy is invariant to rotations. But with the DMRG, it is. Do you do an optimization of the orbitals in the active space, or what's going on?
So without orbital optimization, it's a CAS-CI. So the DMRG calculation would be a CAS-CI calculation, and of course we can switch on orbital optimization as to get DMRG SCF. It's totally analogous to CAS-SCF.
But in a CAS-SCF program, you select one set of active orbitals, and then you don't need to massage those. You're sort of making rotations between inactive and active, an active and virtual. You don't do any active to active rotations.
Yep, it's the same here. So it's totally analogous to the CAS-SCF methodology.
But the DMRG must be variant to active rotations, because
you mean because of the reduced bond dimension?
Yes.
Yep. But for the converged result, it should not be important.
But it might help convergence if you did this.
What helps convergence, and that is an idea that has also been proposed by Reiher, is that you can do orbital rotations in the active space that are advantages for producing proper orbital entanglement patterns that then enhance convergence, for instance.
All right, thank you.
Okay, so these are the examples that I'd like to discuss with you. Vibrational problems, because we have started looking into these only 3 years ago. Something that we have very recently touched upon, and I will briefly touch upon this in my talk too. Pre-Born-Oppenheimer Hamiltonians, which we then call the nuclear electronic all-particle DMRG, where we actually don't distinguish between the particles and treat them all on the same footing. I will then switch to molecular quantum dynamics, where we can then look at vibrational vibronic dynamics, and then also electronic dynamics, which was done in my group by Alberto Baiardi. And then I switched finally to explicitly correlated DMRG by introducing transcorrelated DMRG that is supposed to be at least a partial solution to the dynamic electron correlation problem, because as you have understood by now, DMRG is basically an active space method, and so including dynamic correlation is key. But very expensive in the traditional way, and typically breaks all the advantages of DMRG. For instance, with electronic DMRG, you can treat orbital spaces of 50 to 100 orbitals. But if you now switch to multi-reference perturbation theory, then you're restricted to much smaller orbital spaces, say 30 orbitals or so, because all the higher order reduced density matrices are so hard to compute. Okay, so let's start with vibrational excited state problems. The Hamiltonian you have seen now a couple of times, and so I am quick on this slide here. And briefly remind you how the lattice now looks like. So we are not talking about orbitals any longer, but about modes. The modes that I've picked here are basically the basis states of the harmonic oscillator. From the harmonic oscillator, from your quantum mechanics lecture, you know that it's possible to define ladder operators, and these ladder operators are nothing else but the creation and annihilation operators in second quantization. And then you can use them to do an excitation of individual modes. There is a more general representation of the problem, which is called the N-mode representation. And there's, of course, also a second quantized form of the N-mode representation. By contrast to the representation that you have seen before, now for each of these modes, you have a set of different functions. So the functions for this vibrations don't need to be the same as for this one, right? And that's a more general representation that can be used. When you look into vibrational problems, you're immediately confronted with the problem that you need to address the calculation of excited states. Right? If there is some high energy stretching vibration, then there are other vibrations lower in energy, and you need to come up with a way to target the high energy excitation vibration directly, because you can't optimize the excited states state by state starting from the ground state. That can be done for electronic problems, but for vibrational problems, it's not going to work. What you can use, for instance, is this shift and invert technique that was already discussed in a paper by Garnett-Chan's group in 2007, where you have a shift parameter that is close to your target energy, which is given here in red. And then you solve the eigenvalue problem for this operator, which is the shift minus your Hamiltonian, and you take the inverse of it. And obviously, and then you see it, your target state on the right hand side, you see that it's going to be your ground state, but obviously it can be anticipated that the calculation of the inverse of the operator can be costly. When you do that in this MPS-MPO formulation, at some point you get a solution from the local eigenvalue problem, and then you need to pick the solution that is the right one for your for the red state that you are targeting, and you can do that with an overlap criterion. Okay. Right. I already anticipated that there might be problems associated with it. For instance, taking the inverse of the operator, and the possible solution is the diagonalization of this squared operator. Again, you see there's this shift omega, which is called the folded operator, and we call this then folded DMRG or DMRGF. In fact, you will see that this leads to a stable and robust optimization. The example that I present to you is one of the examples that we had in the paper published on this topic, that's the OH stretching vibration of this dipeptide that you see on the right-hand side. You see here in this picture the convergence of DMRG, and in green the results for the shift and invert technique, and you see it converges, but it's pretty noisy. Whereas with the folded Hamiltonian, it is smooth convergence, smooth and stable convergence. By the way, implementation of the folded operator, which is the squared form, is easy because in this MPS-MPO formulation, remember in the expectation value picture that I presented to you, we had all these blue boxes, and basically what you have in this picture is 2 rows of blue boxes, and these represent then the square of the operator. I should also, so this works and is stable, but it turns out that it can be done more efficiently. There is an algorithm available for targeting states efficiently in some energy window anywhere in the spectrum, and that is the Feast algorithm. And you can also combine Feast with DMRG, which is pretty efficient, as we have described in this paper that we have put on the archive very recently. But let's go back to the dipeptide. Here, of course, we get access to the spectrum. Here you see the spectrum. In black dashed is the experimental spectrum. The harmonic solution is given in red, and the solution that we get with vibrational DMRG is in green. And you see clearly the advantage of the green over the red spectrum. I already mentioned the Preborn-Oppenheimer calculation, so which is basically a multi-particle method where we don't make assumptions on the particles that we treat. So nuclei and electrons are treated on this at the same level. We don't exploit any properties of them. For instance, that the nuclei are much heavier than the electrons, so no Born-Oppenheimer approximation. That can be done very efficiently and very accurately with geminals. Typically, people use, because you need to evaluate the integrals, explicitly correlated Gaussians of various kinds. The group of Ludwig Adamovich has done a lot of work. You can see their review here from 2013 in Chemical Reviews. We have worked on this, and we exploited this representation for our purposes. I should also mention that there are, of course, orbital-based methods, which we can also use in our framework, such as those developed in the group of Hamish Schiffer, but also in the group of Nakai. Okay, so for this nuclear electron all-particle DMRG, this is our Hamiltonian, right? I mean, it's a sort of a simple structure, non-relativistic form, of course. We have all the Coulomb interactions of the electrons and the nuclei. We can make it translationally invariant, so we don't need to introduce a coordinate transformation at the level of the basis functions, which is pretty efficient. That's a neat trick. And we combine now fermionic and bosonic second quantization operators. Here you see the second quantized form of this first quantized representation. And then our state looks like this. Of course, the many particle state has two components, one for the, in this case, simplified, one for electrons, one for protons, but that works in general in this format. And what we do is we first optimize also non-linearly all the basis functions here, okay, with the exponents and so on. But in order to increase the accuracy, then we take the union of all those optimized individual single particle functions and then set up a DMRG representation. So first a full CI type expansion here of these new basis functions. And you see that we can then get combinations of basis functions which are not present in the original representation, which we used for the optimization of the basis. And we use DMRG to get the CI coefficients, right? And so this is NIAP DMRG, and you see results for BH3, where we have a reference result from the Nakai group. These are the dashed lines. You see the Hartree-Fock result, a horizontal line, and here Hartree-Fock plus MP2. If we just do, without DMRG, optimize the truncated CI expansion to get the basis functions, we get these blue results, right? And you see that we don't even reach the MP2 result of Nakai. If we now use this basis to do DMRG, you see that we can efficiently converge to a better energy. So that works, and this is a scheme that we are now expanding into a full-blown multi-particle theory. So I told you that we can also do quantum dynamics. In fact, that was easy to implement in our framework. I tell you why in a second. Before I do so, let me mention that there are actually many variants to do time-dependent DMRG. And the challenges, actually, the general challenges are that this matrix product state representation of our state, when this state evolves, may become increasingly less accurate, which is kind of natural to understand, right? Because you visit structures where the MPS representation changes a lot in such a way that the bond dimension needs to grow. And that is, of course, a killer because the bond dimension determines the effort. The next challenge is that we, of course, want to use a full-blown Hamiltonians, like the electronic Hamiltonian. And so we need methods that support long-range Hamiltonians. And that's the reason why we exploited the idea that is called tangent-space TD-DMRG, which is, you see the equations on the next slide, where the idea is that you can keep the bond dimension fixed, and you kind of, while the state is evolving, find a representation with this fixed bond dimension. What we contributed to this approach is that we made it available, or that we implemented it for the long-range Hamiltonian, for the electronic Hamiltonian, for instance, and that we developed the algorithm for this matrix product operator second generation DMRG program. The working equations look like this for the time propagation. You see the projectors here. The key is that you exploit a Trotter approximation where you decompose the exponential, and this allows you to sequentially apply the propagators so that the tensors are propagated one after the other, and that is in line with the logic of the standard time independent DMRG code, and that's the reason why it can be straightforwardly implemented into such a program. You need to watch out that there is no double counting. And I should also mention that when you consider imaginary time evolution, you can exploit that for the optimization of ground states, which in the end you will see will be key for the transcorrelated method. Let's look at a Hamiltonian. We have already looked at electronic and vibrational Hamiltonians, so let's pick a vibronic Hamiltonian, where the lattice is mixed representation for vibrational modes and electronic states. We looked at various examples, and I pick one here because it's pretty impressive. It's an aggregate of organic molecules, as you can see here. The Hamiltonian is, of course, a model Hamiltonian. where we have per monomer 10 modes that we consider, and then we have 2 electronic states in total. The Hamiltonian has then 72 sides. And this we can consider with our time-dependent DMRG approach. We can even converge, calculate the absorption spectrum according to this autocorrelation function. And here you see the result compared for dimer and hexamer. That is the structure that you have seen on the slide explicitly. The results are obtained for various bond dimensions. You see m equals 10, 20, and 60. For the dimer, you see that already for small m values, the spectrum is already well converged. And you see that even if you go to the hexamer, then the convergence with respect to the bond dimensions, this critical parameter does not change. You can also look at population dynamics. I show you some results here because these are local properties and therefore much harder to converge with bond dimension, as you can see in the different traces here, where m now ranges from 10 to 100. Okay, I just want to make the point that not any quantity really converges quickly with the bond dimension. Yeah, it can be done with electron dynamics. This is the work that I already mentioned was done by Alberto Baiardi in my group. And you can then look at ultra-fast electron dynamics, and probably you're aware of this recent interest into attosecond spectroscopy, and the time-dependent DMRG approach now provides an interesting means to look into attosecond spectroscopy. These are results that Alberto obtained with the electronic version of this time-dependent DMRG approach for these polyacene systems. Here you see the result that he got for the time-independent solution, and then he used the time-dependent DMRG to converge the spectrum. Okay, now let's switch to the last topic of my talk, that is transcorrelated DMRG. I already mentioned that DMRG is an active space method, and so you lack dynamic correlation, and that needs to be efficiently included. The transcorrelated Hamiltonian has been proposed already 50 years ago by Boyce, and has recently been used by Ali Alavi and his group in the context of full CI quantum Monte Carlo, where it can be efficiently exploited. Full CI quantum Monte Carlo in principle faces the same problem, it's also an active space method, but that the transcorrelation works fine there because the FCI QMC approach is a projection approach. DMRG is not. DMRG is variational, and that actually causes a problem. For the transcorrelation approach is very hard to apply to variational Hamiltonians. Now, transcorrelation means the following: we use a correlation factor that is introduces these correlation into the wave function, but is then used to transform the Hamiltonian, as you can see in this equation in the box, right? So you see here the transformed many particle state where we have the correlation factor as an exponential, and then I rewrite this equation so that rather than transforming the many particle state, I get a similarity transformed Hamiltonian. Which leads to, since this is not a unitary transformation, it produces a non-emission eigenvalue problem with all of its consequences. That's explicitly mentioned on this slide. The solution that we found for our variational DMRG, and let me emphasize this again, it's very different from the projection techniques that are exploited in full CI quantum Monte Carlo, is the imaginary time evolution that I mentioned before that can be exploited for optimizing the ground state. So we combined our imaginary time DMRG with a transcorrelated Hamiltonian and arrive at the new approach, which we call transcorrelated DMRG. That can be done in real space and in the momentum space. We first applied that in our original publication last year to the two-dimensional Hubbard model, but we have now in the last 12 months worked it out for the full electronic Hamiltonian. The issue there is that you need to implement a couple of new integrals. We have done that, and we are basically compiling all the results for publication. This slide refers to the question that Roland already had. Standard ordering basically means that you go through the two-dimensional Hubbard lattice where you just put the orbitals on the side as 1, 2, 3, 4, 5, 6, 7, and so on. Feeler ordering refers to the ordering that obeys the orbital entanglement pattern, for instance, measured by this mutual information expression here given in the box. And you see this pattern given here. And when you switch on transcorrelated DMRG, the ordering becomes much more regular in a sense that only few sites are pronounced compared to all the others. So what the transcorrelation, so the similarity transformation, effects in the wave function qualitatively is that certain correlations are reduced. We have seen that before when we were working on short-range DFT, long-range DMRG, short-range DFT, long-range DMRG method that had the same effect. And actually, it addresses the same problem. Okay, here you see some data. Let me draw your attention mostly to this column with the bond dimension M, where you see M is growing. Then there are standard DMRG results in the next column and transcorrelated DMRG results in the column afterwards. And this table should demonstrate to you that convergence is much faster with respect to the chosen bond dimension. This is the advantage of transcorrelated DMRG. Everything that you have seen is actually implemented in our computer program QC Markus. What is currently available is still the old version. We will release all of this very soon. The reason why we haven't done that yet is we are working on a parallelized version, which is almost completed. Those of you who have followed the literature have seen that all the groups that work on such computer programs, DMRG computer programs, have considered parallelization of their codes, like Garnet-Chan's group and also Ursch-Legesar and the people in Prague. And we have done that too. Our paper is not published yet. Once we are finished, which will be soon, we will have a new release where all these features become available, and that new version will be much more efficient than the version that is currently available. The version that is currently available is about an order of magnitude slower than other computer programs, other DMRG programs. That will be fixed, but we always considered it useful to have that version because the capabilities are very large. For instance, there is a state interaction approach implemented in it and so on. So you can do a lot with this program. I conclude to thank all the people in my group for the excellent work. There were very many people who were involved in the work on DMRG. My current team, QC Markus team, consists of Alberto Bayardi, then Stefan Knecht, who recently moved to GSI in Darmstadt, and then Leon Freitag, who moved to Leticia Gonzalez Group at the University of Vienna and recently moved to Belgium to join this company that Toru Shiozaki has founded. Then I have 3 new PhD students working on all these topics, Robin Feldmann, Nina Glaser, and Max Mörchen. That's all I wanted to tell you. I am open for any question that you might have, and thank you very much for your kind attention. I stopped sharing the screen so that I can see you again, if you don't mind.
Thank you very much, Markus. Very, very nice talk. Very, very interesting. I mean, we can see new ways of running calculations, and I think it's very, very interesting. Thank you very much. So please, questions? Roland, do you want to ask something? No?
No, it's Danilo.
Hi. Can you hear me?
Yes.
And hi, Professor Markus. Thank you so much for the nice presentation.
Just call me Markus.
Okay. In your presentation, you showed several applications for the DMRG, and I've been wondering about the computational time of the DMRG. Could you comment about the computational time?
Well, that depends, of course, on the bond dimension that you end up using. For instance, the vibrational calculations, we were very surprised, are fast and efficient. So out of the box, the vibrational DMRG was competitive with all the other correlated vibrational methods, CI, couple cluster, that are available. So that was very surprising to us, because we didn't see that coming. Of course, in the end, you can rationalize why that's the case, and in the aftermath, you understand why it's the case, but we didn't expect that in the beginning. And in fact, we started the project only because it was the program infrastructure allowed us to accommodate these Hamiltonians in a simple way. Otherwise, we would not have dared to tackle it. In general, the large bond dimensions, of course, increase computing time and especially storage requirements. If you compare to, for instance, electronic DMRG to CAS-SCF, our experience is that below 14 active orbitals, a standard CAS-SCF is more efficient. Above 14 orbitals, DMRG becomes more efficient. Just as some rough rules.
Okay, and another question is you highlight in your talk that it's very expensive to include the dynamic correlation in this calculation because the DMRG recover the statistical correlation principle. What do you think the inclusion of the dynamic correlation by using the multi-configurational pair GFT?
Yes, I have been asked this many times. I don't know, frankly.
Because I think in the KC-Max is implemented in FPT2.
So yeah, we have provided an FPT2, and that's the standard FPT2 by Celestino Angeli. Stefan Knecht has, together with Laura Gagliardi's group, worked on the DMRG PDDFT. Yeah, I have no experience with it. And for me, for instance, the question is, if you want to judge whether this is an advantageous method, I would look into the self-interaction problem, for instance. So I don't know whether that has been done. And I frankly, I have not followed the literature too much, so that's why I cannot really comment. But I remember that a few years ago, maybe 3 or 4 years ago, in the papers they always said that they should optimize, for instance, the functionals for the method and so on. And so I don't know where this stands right now. I don't know whether it has been done.
Okay, thanks so much.
Any other question?
Yes, I have a question here. More of a philosophical question. So in the early 1950s, Roten introduced the basis set expansion of orbitals. And we lived in that paradigm since then. All the methods we have developed, more or less, is based on uncorrelated orbitals. And I'm starting to see that we're never going to get the dynamic correlation right unless we start to introduce basis functions in our n-particle basis wave function that is based on explicitly correlated pairs of electrons. Do you have any comments on that, please?
Yeah, so I mean, in the end, this is what the transcorrelated DMRG does, right? It introduces these explicit correlation factors where you have an explicit dependence on interelectronic distance. So the Geminal calculations that I've shown to you, I mean, we have such a software environment, and they are a nightmare. Because so preborn Oppenheimer is a nightmare, and the Geminals are also a nightmare. I'll tell you why. you need to have a recipe to optimize these basis functions, right? If you have atom-centered orbitals, right, you can transfer the atomic, at least the atomic information into the molecule, which is a huge advantage. And that can be difficult for the geminals. And if you use geminals, then suddenly the tricks that you exploit in the derivation of the Slater-Compton rules, right, where there are many overlap integrals which are actually zero and collapse many of the terms of the sum that you have for the anti-symmetrizer, those terms don't go away. And in fact, that is the reason if for this geminal theory that we have developed in the pre-Born-Oppenheimer context, that is the reason why we can't treat very many particles. I mean, for instance, we cannot, with a theory, we can't look at the water molecule. There are just 10 electrons and 3 nuclei. It's just too much. And that is because this sum in the anti-symmetrizer does not collapse. Of course, if you, I remember that you asked me this before a couple of years ago, when you say that the Born-Oppenheimer approximation, you could argue like this, also creates a lot of problems and everybody's working within this approximation. Whereas when you look at the Hamiltonian, seemingly it looks more easy structure-wise, right, than the vibrational Hamiltonian. But then it's the same, right? You cannot exploit any structure of the problem when you construct your basis. And so formally, the many-particle equation looks more simple, but to approximate the state is going to become a nightmare. So my understanding is that there's a good reason why we live with these orbital approximations and with the Born-Oppenheimer approximation.
But there, I mean, to me, the orbital representation is a dead end. We've been trying for more than 70 years to sort of get the dynamic correlation in there, doing couple cluster, and during the last 30 years, they've been starting to go from CCSD parenthesis T to actually doing full T, doing full Q, and it just becomes enormously expensive, etc. And we're living with the notion of basis functions. And the bad thing with the basis functions is the more we put in basis function, the more virtual orbitals that turn up, the more expensive our couple cluster becomes, etc. Isn't it time for us to start actually to simulate the wave function in a more compact way?
Yeah, so if you ask me, there are these 3 solutions. F12 approaches, transcorrelation, short-range DFT. They all address this problem, and they condition the problem so that the CI-type expansion is much more well behaved. Whether you can do more than that, don't know.
But this multi-configurational problem you're looking at, that's sort of an artifact constructions, because you come from a world where you represent things with orbitals.
Okay, but say if you take geminals, then you still need to construct a many-particle state of a sequence of geminals. And these are then basis functions at some point. And then you go back to a CI-type expansion with products of geminals that need to be antisymmetrized.
Yes, of course.
And that, yeah, so that expansion has its issues.
All right. I would be glad to discuss that with you in the future. Thank you.
Yeah, I'm very pessimistic there.
You should never be pessimistic. As soon as there's a problem, there's a work for a scientist to solve a problem. That's a job opportunity.
Yes. Just a curiosity, what about DMRG CASPT2?
DMRG CASPT2?
Yes.
We haven't done that.
I think Stefano Battaglia is working on that together with Stefan Knecht.
It could be. I don't know.
Because you cannot do it with Kissima keys, okay? Right now, I mean, at least with this version.
No. So if Stefan is working on that, we are not working on it.
Is it single state or multi-state, Roland?
Roland, this was a question for you.
Is working on it. It's going to be multi-state.
Okay, good.
But he's been busy the last 2 or 3 months writing a chapter on machine learning on how to optimize wave functions.
Okay. And Markus, is there any relation between the number of the value of m and the number of sweeps, or we can choose it freely? I mean, it doesn't matter. I don't know. I mean, for instance, if I use a larger value of m, should I use a larger number of sweeps?
Difficult to say in general, I would say.
Doesn't that have to do with how entangled the state becomes? And just because it gets larger, it doesn't means it gets more and more entangled?
It's going to depend also on how you construct your warm-up sweep. I don't know. I would always consider in actual calculations these things separately. And the issue with DMRG convergence is that you have seen that in some of the pictures that there are typically these plateaus and occasionally can drop again. And at some point you simply say, well, okay, you're converged, but how would you know? Right? And for that reason, what we actually advocate is that you should never publish a DMRG calculation for a single m value. You should go for, say, 3 values and then extrapolate. Because if anything goes wrong, the likelihood that you would see that is much higher and the result is much better defined.
So it's more important to change the value of m, the number of renormalized states, than the number of sweeps.
Provided that the number of sweeps is large enough. Say 20. I don't know. Not
20 sweeps.
Yeah.
You use 20 sweeps rather than 2 or 4. I mean, just to give some numbers.
Okay.
Markus, could you put the DMRG in sort of a context or a comparison to the quantum Monte Carlo approach? Like the stuff that Giovanni is doing or Alavi?
I mean, in full CI/QMC, you have these walkers, right? That visit basis states. And from those visits, you construct the CI coefficient. And in this sense, it's different. It's very different. The interesting thing is that in the last 15 years, we have seen these 2 different CI type approaches that emerged, which nobody saw coming. But they construct the CI coefficients in a very different way.
Yeah.
So, is there anybody else who wants to ask something? Other questions? No? So, I just have to thank you again for this very, very nice talk and this very, very nice period we have with you. It was really, really interesting.
Thank you very much. Thank you very much for having me. And I apologize so much for all the issues with the time difference that we had at the very beginning.
No problem. So thank you very much. Congratulations.
Thank you. Take care. Have a nice weekend.
Thank you. See you again soon. Bye-bye.
See you soon. Bye-bye.
Bye, Roland.
Tchau, Borin. Obrigado.
Espera aí, Sérgio. Espera aí.